Hello guys, welcome to this new video. So this is going to be question 2 in the May 2023 Time Zone 2 paper 2. So here we're given a graph which shows the variation of pressure times volume with temperature of a gas, and we're also given the mass of one molecule in this gas. So in part A we need to state the unit for PV in SI units. So if we need to state in SI units, we need to use SI units to express these units. So we see also on the units of the graph that PV has units of pascals times cubic meters, as that's pressure times volume, but this is not good enough yet, as we need to simplify it a little bit more. So we know that pressure is just force over area. So pressure will have units of newtons per square meter, like this. So now we just need to substitute this in for pascals, as a pascal is just a newton per square meter. So the units will just be newton per square meter times meter cubed. This will be newton times meter, but a newton we can still simplify, as that is not an SI unit yet. But we know that F equals MA, so a newton will just be kilogram times meter per second squared, as kilogram is for M and meters per second squared is for acceleration. So we will see that this is equal to kilogram times meter per second squared times meter. So the SI units will be kilogram, meter squared, and seconds to the minus 2. So this is how we can express it in SI units. We always just want to look at some equations that will introduce SI units instead of the unit we currently have. All right, and then in this part we need to use the graph to deduce whether the gas is ideal or not. So what we need to remember here is that an ideal gas is a gas that follows the ideal gas law, which is quite intuitive, I think. So, and the ideal gas law, if we look in a data booklet or we just know it, is PV is equal to nRT. So this equation needs to hold for a gas to be considered ideal. If this is not true for a gas, then it will not be ideal. So the simplest way probably to use this equation here is to rearrange it a bit. So we can say that PV over R, well, PV over T is going to be N times R, which is a constant, because the number of moles and the gas constants are two constants here. So PV over T must be a constant number. And so this is what we just have to check here on the graph. So we can pick 2 points. I probably would recommend to choose 2 points that are easy to read off the graph, that are like on the intersection of 2 grid lines. This will make your life a lot easier. So this here is at 60 degrees Celsius and 5 times 10 to the 2 of pressure, and here it's 100 degrees and 5.6 times 10 to the 2. So we just need to plug this in and see if we get the same values. So for the first point, we had 5.5 times 10 to the 2 divided by 60. Only thing is that the ideal gas equation only is true for SI units, and the SI unit for temperature is Kelvin. So we need to add 273 to it, and this will be 1.5. And then we calculated for the other point as well, which was this was 5.6, and this was 100. So I did it the other way by accident. I wanted to calculate this point first and then the second point, but I ended up doing it the other way. So then this point will be 5 times 10 to the 2 over 60 plus 273. And then this will also be 1.5. So since these two are equal, it's an ideal gas. We could have also seen this from the fact that PV over T is just the slope here, and we see that the slope is a constant value. Although I think we did need to do this calculation as it's worth 3 marks, and I'm not sure the IB would give us 3 marks just for writing that the slope is constant, or we would have to supply them with some serious explanation to convince them that we earned the 3 marks. But if you know that the slope is constant, you can just prove it as well with a little calculation. And then in the last part of this question, we need to calculate in grams the mass of gas. So, and we were given the mass of one molecule. So from this graph, we can determine the number of molecules we have. And if we have the number of molecules, then we can just multiply it by the mass of one molecule, and then we'll have the mass of the gas. So the question is, how can we determine how many molecules we had? Well, if we first find the number of moles we have, then with Avogadro's number, we can convert to number of particles, as a mole just says how many particles we have in a given space. One mole has 6 times 10 to the 23 particles. So we need to calculate the number of moles, for which we will again use the ideal gas equation, PV is equal to nRT. So from this we see that N will be PV over RT. So again, we just need to plug in the values. So what we can do is take one of the points we have already chosen. So let's take the first point, for example. Then the PV will just be 5 times 10 to the 2. And then R is just the gas constant, 8.31. And again, we will have 60 plus 273. Because again, we need a Kelvin here. This will give us 0.18 moles. And we know 1 mole has 6.02 times 10 to the 23 particles. So from this, if we do 0.18 times 6.02 times 10 to the 23, we will find that we will have 1.09 times 10 to the 23 molecules or particles, same thing, like this. And then we know the mass of one molecule. So if we have this many molecules, well, then again, we just need to do this multiplication here. So the mass of the gas will be 1.09 times 10 to the 23 times the mass we were given, 4.7 times 10 to the minus 26. This will give us a mass of 5.1 grams. And this is how you solve the second question in the May 2023 Time Zone 2, Paper 2. And see you in the next question.